okay?
Yeah, it's a little bit better. When you were moving it around, we could hear it. So maybe if you get close to the microphone.
Okay, yes, ma'am. Yes, ma'am.
Okay.
Okay, good morning and good evening. I would also like to thank the previous speakers, Jorge and Rabia, for making my task easier by explaining the importance of islanded microgrids and also shedding some light on physical fault right through of converter operation. So I should, Abdina, take the pleasure to present before you my work based on resilient control and operation of interconnected cyber-physical microgrid clusters. I'm working under the supervision of Dr. N.P. Pari at IIT Roorkee. Next, please. So we will just have a brief discussion, an outline of the work that we are doing here. We would have an introduction on cyber-physical systems, and then shortly we will move on to two works that we would like to present. That is on basically on DC microgrid clusters. We are working on false data injection analysis and man-in-the-middle attack. These attacks have been very thoroughly studied with respect to IT infrastructure, but its contribution with respect to power electronic converters is very limited and are being explored in the current trends of research. So let's move ahead. Next. Okay, this is a small, brief idea about graph theory in which agents are connected to each other via a graph, and their equation is shown as xi dot is equal to ui aij xg minus xi, where xg is the neighbor of ith agent, and hence the cooperative control also explores this graph theory. And there are two objectives of cooperative control, that is synchronization and tracking. Synchronization is for systems which do not have a leader, and tracking is for systems which have a leader. So there are one equation and those two theorems that govern this graph theory. We will discuss it later. Let's move ahead. Ma'am, next. Yeah. So cyber-physical systems from an electrical perspective can be considered as the confluence of many things like electromagnetics, information systems, circuit and control theory, and graph theory. Ma'am, next. Now let us have a classification of the attack with respect to power electronic converters and the region of operations of the power electronic converter. So the data manipulation attacks are basically categorized into deception and denial of service. Deception has false data injection analysis, and the other categories are stealth, covert, and replay. Under false data injection analysis, which is a concentration of our research here, we have the positions of the FDIA in sensors, controllers, and communication links. For DOS, it can be an aggressive attack of just suspending all the information links, whereas there can be another alternative known as man-in-the-middle attack, in which can be seen as somewhat hijacking the communication channel between two links and then completely replacing the data and sending some arbitrary data to the neighbors. So based on that, we have classified into unidirectional and bidirectional. This could be more elaborately understood from this graph in A that we have shown here. In the one which I have used with color nodes, that MITM would completely hijack the channel and start introducing attacks in both the directions to both the nodes. Then it will be a bidirectional attack. However, it is just one way, then it will be a unidirectional attack. FDIA is different from MITM because it overrides the set of original data. And DOS would be complete loss of the communication link. And what's a Byzantine agent? Any agent which has been compromised and starts sending malicious data to its neighbors. So after understanding this basic terminologies, let us have some light on the converter operation in figure B that I have shown here. So under normal operation, the normal operating region for a converter, or let's say any inverter, would be its maximum operational region for the voltage and current. So that entire region has been shaded in blue. And for the optimal operating points, we would like the converter to operate at its average rated voltage and rated current. So that would be its optimal operating point. And now the operation which I would like everybody to focus on is a communication fault right through operation. It is different from physical fault right through, because for physical fault right through identification, the indices are different and the operational action taken is different. For communication fault right through, we actually analyze the information and we decide whether we can provide some trade-off and let the converter sit there until and unless the thresholds are violated. That is, Vmax and IDC max are violated. Next slide. And next slide, please. Okay. Thank you. So here we would like to discuss all those things that we have previously understood with respect to interconnected DC microgrid cluster operating under man-in-the-middle attack. So as you can see on the picture on the left, we have taken up 5 DC microgrid clusters. Each DC microgrid cluster has 4 DC-DC converters, and we have assumed that there are circuit breakers which would be operating on the over-under voltage protection, and the converters are equipped with the overcurrent limiting protection. So we can move ahead now. Okay. So these are this is the attack model, XC and V reference K. I will tell what is the importance of it later in the slides when we discuss the control theory. What we have done, so let us just have a small idea of what we have done to identify the presence of any malware. So let us formulate an idea that attacks could be uncoordinated and coordinated as well. So through uncoordinated, I want to say that the neighboring information difference xj minus xi will not become 0, whereas in coordinated attacks, it will become 0. So we have focused now again on uncoordinated man-in-the-middle attacks. So what we do is we take up an error index EGI, as I have mentioned in the slide. EGI is actually the difference between the present ith agent and its neighboring jth agent in current and in voltage both. And then we have formed an attack recovery factor, which is whenever, and we have put certain thresholds. Whenever it violates the upper threshold, it will be, for example, whenever it violates the upper threshold, it will get activated and it will say that yes, attack has occurred, that is 0. And whenever it is within the threshold, lower than the threshold, then it will be, okay, it is a normal operation, so it will continue the normal behavior or operation of the control theory. However, if it is between 2 thresholds, that is upper and lower, then it would have a selective cancellation or selective allowing the data. So next we can move ahead. So to have more pictorial view of what we have done, here the picture on the left denotes we have constructed primary, secondary control layer, local tertiary, and global tertiary control layer. So there are multiple layers of control in operation. Primary control layer, as we know, it performs a basic function of current and voltage regulation. And the secondary control layer helps us to overcome the negative effects of group control, because it does not, if we try, it is like if we try to have an effective current sharing, we cannot have an effective voltage regulation. So these things are minimized with the help of a secondary control layer. Then we move on towards local tertiary control layer. Is actually a reliability layer for the global tertiary control layer. The global tertiary control layer helps us to exchange power with the neighboring clusters. So as I said, DCMG1, say V1 cluster or one community of microgrid. DCMGN is the nth community of microgrid. So the inter-microgrid power sharing will be facilitated through the global tertiary control layer. Here we have shown the operation on the right-hand side picture. Operation of these microgrid clusters, 5 microgrid clusters, and in the presence of single leader or multiple leaders. And we have also tested in changes like and DCMG2, whether the other microgrids are also dispatching power to it or not, and whether the voltages are maintained within 380 volt or not. So for this test, we have taken up 380 volt as the reference voltage. So everything is in place. Now let's move ahead. Now we start investigating the effect of intrusion on the normal operation. That the intrusion is from time period t is equal to 1.2 to 1.5 on one of the converter. So we see that what has happened is it is disturbing the synchronization or the consensus operation, and it has also disturbed the synchronization at the DC microgrid 1 level as well as on the global level as well. So how do we eliminate it? We then activate the attack recovery factors. So we can see that the next figure indicates towards its mitigation. So when the attack recovery factor starts operating, it just identifies the component which has been attacked, and then it temporarily suspends the information to its neighboring converters. So what happens is it is still in operation physically, but on the cyber level it is disconnected. So that is what we meant by saying that it will have a communication fault right through. By making this operation, we ensure that the healthy nodes achieve synchronization, and after the attack has been removed, then again that unhealthy component or the compromised converter could again be brought back into normal operation. That could be observed from figure number 7. For instance, 1.5 to 2 seconds, the attack has been removed and the consensus operation has been achieved. Now, figure number 8, we had just made a comparison of operation with one of our papers in IEEE Systems Journal, in which we had not taken into consideration MITM attacks. So we just wanted to show that the FBI indices, that the indices developed for false data injection, cannot identify man-in-the-middle attack, and we need to have certain modification in order to facilitate the operation. Okay. Now we move towards a real-time implementation. We have chosen RSCAN or RTDS for that. What we have done is we have taken 3 subsystems in 3 different racks in order to imitate an actual microgrid community. They would be separate from each other geographically. And so these 3 microgrid clusters have been taken up in 3 racks, and then they are connected via an IRC, inter-rack communication switch. And we can move it. These are the modeling parameters in RSCAD, and we have done an intrusion in one of the leader currents which is entering the global layer of control, and then we are trying to show in RTDS that the ARF which we have modeled is effectively identifying the compromised link and is providing a communication fault right for that time duration, and is letting the other microgrids to operate safely until the cessation of attack. Next, we can move. Okay. So what we have done to have more realistic approach to what we have proposed, we have gone for a controller hardware in loop implementation, in which the global tertiary layer is actually a centralized controller. So what we have done, this global tertiary controller we have implemented on FPGA based WaveIT, and the other microgrid clusters, as I've shown in the figure, if you could see, there are orange and green nodes. So these nodes have been modeled as 3 different microgrid clusters in the racks of RTDS, and the global tertiary controller, which has been outlined in red, is modeled in WaveIT, FPGA based controller. Then we have exchanged those signals through analog in and analog out, and we have the same test case that we just discussed previously. We have tested that whether this thing is being correctly identified even in the presence of certain delays that we may have while communicating the signals from WaveIT to RTDS. So yeah, we had a CHL validated of that same operation, and we can see that the reference current from the microgrid cluster 1, which has been subjected to malware, has been effectively identified and separated for that time duration. We can move ahead. These are the parameters, control parameters and thresholds that we have defined for our work. We can move ahead. So this is the second work that I would like to discuss. So basically, when we talk about power electronic converters, most of the time we ignore that there is a battery sitting behind the back. So when we design consensus controls based only on its current of the battery, then we are doing actually injustice to the battery operation, because the operation of the battery interface power electronic converter should be based on its state of charge. But there is a trick here. There is a trap that if we take up state of charge as the consensus variable, then there might be discharging and charging cycles between the batteries in a battery pack because of different SOC levels. So what we have done, we have taken up a modified version of SOC, which is represented by the capital SOC J, and we have tried a consensus operation on this state of charge variable. The considerations that we have taken, yes, the modeling parameters here is mentioned in table 2. In this work, we have taken a different approach. We have supposed that why should we stick for only one kind of converter operation? So what we have done is we have tested for both the kinds of converter operation, for in buck mode as well as in boost mode. So let us go through buck mode and then we would proceed to boost mode. So here the formulation of the attack detection is through confidence factors as mentioned in CF for SOC and CF for voltage. And then we have multiplied those two factors to formulate to get an ultimate confidence factor for the data received at the jth terminal. So we can move ahead. These are the control equations governing the structure and the confidence factors. We can move ahead. Okay, let us take just one example. Here the operation. Okay, let me focus on figure 15. So if we see that here we have taken up a study case in which there is an attack on the voltage information of converter 1 in DC microgrid. Here because of the operation of the confidence factors, the malware or the affected converter, which I have encircled in red, is effectively identified. And it does not false trigger during the converter plug and play operation, which is taking place between t is equal to 1 to 2 is equal to 2 seconds, whereas t is equal to 1 to 1.8 seconds, there is the presence of an attack. And subsequently, there is a load change. The basic idea was to show to the readers or show to the reviewers that there is no mall trigger. The thresholds are set in such a way, and moreover, we have used filters so that a false trigger does not happen. Ma'am, you can move to the next slide. Ma'am, next slide, please. Okay, so here what we have done, the same thing, we have tried to validate the structure using boost converters in a cyber physical structure in RTDS. As we can see, we have chosen, there's an attack on the links of converter 2, and it is effectively identified by the operation of the confidence factors, which you can see in figure 17D. Next slide. And what we have done that in practice, these microgrids would be actually connected together for improving the reliability of the distributed energy resources. So we have taken up again the similar manner, community 1, 2, 3 in different racks of the RTDS, and then we have started injecting concurrent attacks on different microgrids and tried to see whether they are operating effectively or not. So the confidence factors detected successfully and suspended temporarily, and then again bring it into operation after the cessation of the attack. So one important thing I wanted to mention here, for this article, for this work, we have actually chosen both kind of data manipulation attacks, a hybrid of false data injection as well as man in the middle. Okay, we can move to the next slide. Ma'am, one more tab if you can make. There is a figure that should appear, yes. So I would, previous. So we like to conclude that the operating point which I showed in the last work is not optimum, because it was based on SOC consensus true, but the operating point is not optimum because optimal points would be reached only if you design a global controller. So that is what we are working on, designing of a global controller based SOC. And a few questions have been raised to us actually. that how do we identify, how do we differentiate cyber faults and physical faults. So we are also working on that, but we know for certain that cyber indices cannot be simultaneously used for identification of physical faults. So we are presently we are working on the idea of having the rate of change of current for identifying faults in a DC microgrid. Simultaneously, we know that the work stands challenged more because it has not been investigated from the perspective of AC microgrids, which are going to be more practical, or the research would be incomplete without it. So what we have, we are also working on modeling of distributed secondary and global tertiary control layers for AC microgrids, and hopefully we would present to you something new in the next time when we meet. Thank you. Any more questions? Any questions or doubts you could ask?
All right, we have several questions already. What is the criteria to determine the voltage threshold upper and lower bounds to differentiate the attack in normal operations?
Oh, no. Here I would like to make this thing clear that we have used the voltage thresholds, upper and lower voltage thresholds, for communication fault right through. But for the identification of attack, if we recall, I have said that we are trying to identify the difference between the peer-to-peer information. So it is not voltage threshold, it would be rather the difference in voltage thresholds.
Okay. If you have other questions, please put them in the chat. Which type of control method do you utilize for your inverters? Mm-hmm. Are they grid forming or grid following?
Yeah, for inverters, we are utilizing a grid forming control, but we are also making a correction for the droop control by using a secondary level. So we have modeled up to secondary level controller.
And last is a given battery pack, especially a given battery pack of especially lithium ion type of has charge balance circuitry. Why do you need consensus-based algorithm here?
Oh, yes. It already has a charge balance circuitry, but it is within the cells of a battery pack. I'm talking about two different battery packs. Suppose it is located in my house and another is in my neighbor's house. So on that basis.
Okay, any follow-up questions for Satabdi? All right, here's some other additional references as well. Okay, thank you very much.
Thank you all. Thank you, ma'am.
Okay, so let me stop sharing that, and then I will now bring up the last talk here. Okay, so our last